Okay, so let me give you my solution. So this is the model that we had before. And what I want to do is I insert a function here. And the function looks like this. Look-ahead layer of x is splice of x and the future value of x. Does that make sense? Any question? Yeah?
What's this default hidden activation?
Okay. The default hidden activation has to do with the, because we're looking at, in this case, the future, and also past value looks at the past. What do you do when you look beyond the sequence? So what is the past value of the first value? Right? You have to tell it somehow what that is. And this basically tells it that it should take 0.
Oh, I see. So this is essentially what then it is for sort of heavy.
Yes, exactly. And at the moment, this can only be a scalar, can only be a constant, but very soon it will be possible to just pass another node there, and then you can very easily build sequence-to-sequence models with this as well. Okay.
It's a base case of the recurrence.
Yes. Okay. So let's just read, let me just run this while you're working on it. You would have to take that out, yes. Yeah. You can just comment it out or delete it out. Let me just type this here. So if you take it out, it's like this, right? You can just comment it out. So.
Is this working for a GPU model?
If you comment out the batch normalization, it will work. Oh, with the GPU, if you have a GPU, you can use.
It says CPU is not.
Yeah, then please comment out the batch normalization. Yeah, if it's still there. Yeah. Yeah, my apologies for the confusion about CPU versus GPU. The problem is that, you know, when we do this in our team in Microsoft, we all have GPUs in our machines, and, you know, it's all fully set up. It has all the dependencies on it and so on. It's very hard to, you know, test it. We can't even find machines to test it, to be honest, to find a machine with a fresh install. Which one is 0? The hidden activation? So when you're looking at the next node, what happens for the last word of the sequence? At that point, so let's say the second last value, you will get the embedding of the last word, right? And for the last step, you will get 0 as the embedding. And whether 0 as an embedding makes sense or not, that's up to your task. It doesn't always make sense, right? So that's why you can specify different values. Somehow the default in there is 0.1. Which has been found in past experiments to be a good default, but it's not universally true. So that's why at the moment you just have to always specify what the default value is. Okay, so it finished. Let's see how it's doing. And it came down to 2.0.
Can you show your command again?
Sorry?
Can you show your command?
The command. So in my case, I added this to the path. The file name, right? Because that's I run a pre-baked file. You would run this. It's not working for you? Do you want to have a look, Amit? Maybe see it. Yeah.
Got a question?
Yeah.
How does it compare, say, to CRFs?
I'm sorry?
How does this approach compare to CRFs? This task?
I frankly, I have no idea how it compares. I didn't try with this particular configuration. It's a common thing to do, actually. Yes.
Common.
Yeah. Sorry. This is more about this, getting the software to work and so on. So the idea is that you use your own config, the existing config file, and make modifications.
Yeah, could you show it again?
Oh, the config file. Yeah. Okay, so the addition is this, right? You put the function into the sequence here, and then this is how you define the function.
Thank you.
So it gets passed in as X.
Aha. So what sequential does is it starts with query and passes this to embedding layer. And whatever comes out of that, the result of that, then gets passed into look-ahead layer. And then look-ahead layer concatenates these two values, and that result then is passed on, in my case, to the batch normalization layer.
So when you put just colon in there, it's taking the results of the previous.
Yes, and syntactically the colon is just indicating this is an array. So what you see here is an array of 6 entries. The first entry is embedding layer, the second is look-ahead layer, the third is batch normalization layer, and so on, right? And then you pass this array of 6 functions to sequential, and sequential then basically runs whatever input it has. Think of it as a for loop, right? It loops over this array, starts with the first value, runs it through the first function, and so on.
So these functions are shown like a pipeline over here.
It's a pipeline, and you can think of it as like when you're familiar with Unix shells, for example. Think of it, you're writing a script that consists of multiple Unix commands in a row, but without an input file. So say grep vertical bar, awk vertical bar, sort. And you save that as a script file, and then you execute that script file by piping some data into it. So this is what the sequential operation does.
What if the look-ahead layer needed 2 parameters and you couldn't do it like this, like skip?
Correct. If you have 2 parameters, you have a problem. So there are ways, so for example, whatever comes out of a function can be a record or an array of values.
Right.
So you could have, I have one situation where I basically, I apply 2 different functions to the same input. And then it would output, instead of a single value, it would output an array of 2 values. And then you can pass that to splice, for example, as a next step. But it's something that you, so basically it's not that you output 2 values, but you output 1 value that actually consists of it's a data structure.
Okay, so it's like a table and you can say, okay, I see.
That would be the idea, yeah. Okay, so I would like to move on to the next one. I think I have to move on, actually. So the next I would like to do is, well, we have now seen that looking ahead by 1 word is a good idea. How would we look all the way to the end of the sentence by using a bidirectional model? So what I would like to do is now, in addition to the left to right LSTM, let's also run a right to left LSTM. And then take whatever the output is of both of those, stack that together, and that output then is what we're using for classification. Okay? So, what? Let me see. So, yeah, I should give you an example of something similar. So here is a way. Here's a function that applies, for example, a linear layer and a batch normalization layer, and then we have the apply function that executes these 2 functions. And what you're creating should have very similar structure, but the first one would be a recurrent layer. The second is also a recurrent layer with in the backwards direction, but then this function will look different. At that point, you will have to splice something. So is the task clear?
Something, it means that that's just a label for that function, right? It's not going to execute it at that line, right?
No, but it instantiates something. So it implies that this linear layer here has a set of parameters associated with it. Okay. So if you then say f equals linear layer, g equals linear layer, they will be separate instances. Okay. And if you pass then, if you apply the same instance, if you say f of x, for example, which would be a strange thing to do, means you are running the data through exactly the same set of model parameters twice.
Yes.
Right? But if you have f1 and f2 and the expression is just the same, but there are different variables, they will be different parameter sets in there.
Right. So basically, but the actual computation happens when you are applying them to each other, right?
Correct. And the real computation happens later on and when the SGD process kicks in and so on, right? So this is still sort of a symbolic description of what you're doing. Did anyone succeed with the function? Oh, and before you run this, please also do one thing. Please remove this one-word look ahead again. And also change the hidden dim parameter. That's a bit up there. Hidden dim equals 300 in your case. Please change that to 150 to make the model a bit smaller. It's the recurrence that you're going to replace. So the look ahead goes away, and the recurrence you replace by this more complicated bidirectional recurrent layer. Okay, I'm going to show you the answer. And in the meantime, I'm going to start running. Okay, so this is the answer, right? So you define your own function, and internally you create two layers. You create a recurrent LSTM layer with this go backwards flag false. That's what you got from the original model. And then you create another one with the go backwards flag equals true. Now these are layers with built-in parameters, and now your apply function would basically utilize those two functions. It runs x to f, it runs x through g, and then splices, which means concatenates the result. And that is the function that you're returning. So now you can put this into the configuration here. And now I realize I already commented out the batch normalization. Okay, does this make sense? Do you have questions about that? Okay. So let's see how it's doing. Oh, it's still training. Okay. One more. Oh, is this running more slowly when it's in the background or something? Window. That'd be smart. Yeah. You actually find that there is a file called _solution3. You can also find it there.
Maybe I'm just, I feel I can't tell how stupid I'm being, right? How have you told the configuration the data is sequential time-based?
Ah, okay. That comes out of the, just out of the data. This is, because this is how you define your data. Let me show you the actual file, although it's going to be a bit more messy. Okay. Does Notepad work on that? It is test CTF. Yeah. So this is the actual file that you have here. I'm not sure if I can make this bigger. No. Okay, so I hope you can read it. You can see that all these tokens begin with a 0. So this is the syntax that tells the reader this is a sequence of that many tokens.
So it just recognizes
from the input
as a
Correct.
And then feeds it to the network in the order. So there's an implicit the order in which they appear in the file.
Yes. And this is one.
That's just part of your data reading infrastructure.
Correct. Yes.
All right.
Yeah. And for example, if you have speech reader, then the format will be different, but it gives you exactly that. So the data format itself describes what the sequences are. And so you can't really see it in the original file because this is not properly aligned here. Let me go back to this. I prettified this a little bit. Here you actually see multiple sequence, right? So this is a sequence that has a different length. So this actually says that sequence 19 has, well, S0 has, I don't know how many this is, 12 steps. S2 has 12 steps, but S1 only has one time step. And you can use the same format, for example, to build a sequence-to-sequence model, where maybe one column is an English sentence and the other column is a French sentence, and they just have different length. And then whichever is shorter just lacks the corresponding entries. So I'm going to look at the results. So you see now we ran the bidirectional model, and it also gets pretty much exactly the same error rate as the look-ahead model. So this just shows there's two ways of giving the model some future information, either by just a single word or by the entire recurrence.
I didn't have the GPU optimization, so the difference between it was a lot bigger, actually.
Which one is a lot bigger?
The difference between this one to look at was really large.
It's pretty large.
2.2 to 1.9.
Oh, okay, okay.
Without the GPU optimization.
I see. Okay, yeah. Okay, thank you. It's good to know. So I want to do one last one. So now we're going to make use of this column here. Now we're going to change the task. So far the task was for every input word, you're going to produce an output label. Now we're going to change the task into, for the whole sequence, give me one output label. So in this case, it should say that this query is about the topic or the intent flight. I want information about flight. And there are other intents there. We can just go back to the file. Where did it have? I have it here. For example, this one has flight, this has airfare, this is flight again, and so on. So what I would like to do is I would like to build an intent tagger instead of a slot tagger. Okay, so we already have a pretty neat slot tagger now. So let's just modify this. And so what we can do is, okay, how do I explain this? So the LSTM is now going to run over the entire sentence, but then we will only take the last hidden state of that recurrence and pass that to the dense layer. And how do we do this? Well, there is an operation in CNTK called last. In this case, you have to give it this namespace here. And what that does is, if you give it a sequence, its output will be the last item of that sequence. So please try to take the configuration that we had just now, or maybe the previous one, and modify that so that you get the last item. And if you're running the bidirectional one, you also need to, for the other one, you need to use first. So for the backwards recurrence, you need first. So modify the code to put in this last and first calls around the recurrent layers that you're running. Yeah, we definitely have to do it. Yeah. So if you successfully did this, let me just show you the answer because we're sort of running a little bit behind. Which hands on here? This will do hands on. So all you need to do is you insert bs sequences.last before the call to the recursion, and here you call first before the other recursion. And if you run this, you will now get an error. This is not working. So you did it right, but you will get an error. And the error will be this error message here. Dynamic access layout is shared, but layouts generated are incompatible. So what does that mean? it means that now we're dealing with two different inputs that have two different time dimensions. Right? So this goes to your question. So the reader has inferred that the first one has 12 tokens and the second has 1 token. But CNTK at that point assumes they're all the same, and it will give you an error message. So in order to resolve that, you need to tell explicitly that there's more than one time base or time axis in the system, and which inputs use which. So what you need to do is you need to augment the definition of the query by doing this. You need to define a so-called dynamic axis object that represents an additional time dimension. And then you need to declare for this input that it should use this different dynamic axis. Now, technically, you can do this for both, because we have two different axes here. So you could declare 2, but turns out CNTK has 1 default axis, so it's actually enough that you only change one of them. And if you add this also into the code, we're going to show you what that looks like. So this is the change here. And if you do that, then you will get a result like this. So okay, so it finishes and it comes up with a classification result of about 11%, which is not very good. And the reason is that you see here we only have. Let me go back to the training. Okay, so what you see here is that now we no longer run over epochs that consist of 36,000 samples, and the reason is that we have more inputs than outputs, but what actually influences your training criterion is no longer the 36,000 inputs, but it's only about 2,700 outputs, because every single sequence that consists of multiple tokens has only one label. So this is the number of labeled tokens that you have here. And you can imagine you ran this on, in total, this is 8 epochs times 2,500. So this is like 20,000 samples that it has seen. So it's not really a very large training set, and we haven't really converged much. Okay, so,
I have a question.
yeah?
So you have 2 tasks going on here.
Yeah.
And so are you training 2 different networks, or?
No, it's the same network that sort of has a split. So you do embedding. And instead of a single recurrence, you basically have a forward recurrence and a backwards recurrence. And they're running sort of in parallel. And then you merge the results with a splice operation. And from that moment on, it's a single path. So the network sort of splits. This is the structure of the network that you get.
Sure. And then for the, so here you're learning the intent of the query.
Correct.
So this is different.
Oh, sorry. This is a different task. I'm sorry. What? Yeah. That's a different task, yes. So we're no longer learning the slot tagging. We're now only learning the intent. You could imagine using a multitask learning. So that's maybe an interesting task for you. The way to do that is actually very simple. You just define 2 CE criterions. You say CE1 uses the slot tagger and CE2 uses the intent tag as a label. And then you interpolate them. You say CE is equals like 0.3 times CE1 plus 0.7 times CE2. And that's what you're running. And then you have a multitask learner that actually learns the network for both tasks at the same time. Very, very simple. Okay, so that concludes the hands-on that we wanted to do on spoken language understanding. We have another one. Obviously, we don't have time for that we prepared for image recognition. So on the same tutorials page, you find the link to that one. So feel free to do that on your own time. Now we would like to move on with Amit and just spend the remaining 10 minutes to talk about where CNTK is going and what the future Python and C++ APIs are going to look like.
Okay, so as you saw in the lab sessions today, currently CNTK is available in the form of a binary executable, and you define your models and you drive your training using this text configuration file. So this talk is going to be a preview of the Python, C++, and .NET APIs that would be made available as part of the V2 release of CNTK. So these APIs basically provide you a programmatic interface to let you programmatically define your models and drive your training. So I'll not be going into too much details of the actual APIs themselves, but just give you a sense of what the key design goals of the API are, and what tasks that you'd be able to accomplish using these APIs that you cannot do using the current form of CNTK. And finally, just take a very quick peek at the actual APIs themselves. So it has been an explicit design goal of CNTK to allow users to very concisely define and drive the training of their models. So we use a custom scripting language that you saw, BrainScript, and since we have full control on the syntax and semantics of the language, our model definitions are very terse, right? All the hyperparameters of the training are specified using simple config settings in a text file, which means there is no boilerplate that is used that the user has to deal with, right? And as somebody commented earlier in the day, they found BrainScript and the text config thing beautiful. I mean, this is exactly what we feel as well. It allows users to create arbitrary neural networks and train them without requiring any programming, right? So this is, you can iterate very fast and operate at a very higher level. However, this system has its own shortcomings. The biggest one is that it's very hard to interoperate using this binary and config file from external code and libraries, right? So if you wanted to implement something like reinforcement learning, where your core training has to interact very closely with an external simulation environment, having to launch an EXE inside this external simulation environment is not suitable, right? So this is somewhere where this closed form is unsuitable. Using a custom scripting language means we do not have any tooling support, so you don't have any IntelliSense, you don't have any code completion. If you make errors, the only way you detect them is by going through the log file errors. And finally, it's very hard to extend the facilities of the toolkit. Any new feature that you want to implement, you have to go and do that in the core C++ implementation of the toolkit. So the V2 library provides .NET, Python, and C++ APIs, which offer a programmatic interface to the computational as well as the training capabilities of the toolkit. And these are meant to coexist with what you saw today, and users will have a choice of either using the library form or to use what you are using today in the tutorials. So as I mentioned, when you're trying to do reinforcement learning, the problem is the only way to ingest data in the toolkit today is have it in one of these formats that are understood by the built-in readers of the toolkit, right? And as part of the V2 library, we have designed in-memory data interfaces that allow you to easily and efficiently pass data into the toolkit and also extract computation results out of the toolkit. Secondly, you have programmatic control over the core training process. And so combining this with the data interfaces, now you can easily implement these advanced algorithms like reinforcement learning, right? Where the core training is happening inside an external simulation environment, right? So you simulate something, you get the rewards, you pass that to the core training process, you learn from those rewards, and then go back to the simulation environment. So this is something that you could do with the API because it allows a much faster rate of iteration with the core training process. Also, extensibility has been a major design goal for our library. So we wanted to, the V2 library makes it very easy for users to extend the core facilities of the toolkit by just writing their own Python code. So you don't have to do this in the core C++ implementation. You can implement your own tensor operation by writing your own Python code, or you could implement your own parameter training algorithm by implementing a simple learner abstraction, or you could implement your own reader by extending a simple Python abstraction for data reading. And these would compose with the rest of the built-in facilities of the library, just like anything else. So we'll look at this more closely in code very shortly. So having the toolkit available in the form of a library means that you have the tooling of the host programming environment available to you. So you could use IntelliSense and code completion to detect semantic and syntactic errors early on. And higher level semantic errors like the model definition error that we saw earlier are also easier to catch and diagnose, because now you can actually see them in the form of exceptions inside your IDE, which means you have all the context of your program available. and you can more easily diagnose what the source of the error is and fix it, compared to having to look through a log file. Also, we have a fully featured C++ API. The C++ API, the simplified C++ API that we provide, is not just meant for eval. You can do training with this. So if you wanted to implement online learning by actually deploying your model evaluation using the C++ APIs, you can use real-time data to also learn or refine your model inside your serving pipeline. Because typically using Python or some other form is not suitable in the serving process. Finally, having these basic building blocks available in the form of a library allows the community to develop high-level components, right? And today you can do that for BrainScript. BrainScript allows you to create these high-level components for model definition. But now, since the other parts of the training, like data reading and tensor operations and the learning algorithms, all of these can be extended and also be offered as standard library components developed by the community. It does not have to come out of the core toolkit. So now let's look at a simple deep feed-forward network and get a sense of what does it look like to define models using this API, and how do you drive the core model training process itself from your code. So the code on this page is basically the model definition code. This should look familiar. This is doing the exact same thing that you were doing in your BrainScript model definitions. So this function at the top is basically instantiating a fully connected layer. So it basically takes a symbolic input and projects it using the times operation to a given dimensionality, then applies the bias operation here, then finally applies the nonlinearity, and now it returns a function which is basically a high-level function that adds this, this fully connected layer on top of the input, symbolic input. And this function at the bottom, again, does the same thing. It takes a symbolic input and it actually stacks. So it calls this function repeatedly in a loop to stack multiple of these fully connected layers to form a deep network. Right? And finally, we apply this output projection, because this is a classification model that we are building. So it projects the output of the final hidden layer to the dimensionality of the number of output classes that you are trying to predict. And now this is code. This code is basically how you would drive the core training process from your Python program. And earlier you were doing this in the form of this simple SGD block in the text config file, but now you have programmatic control over this process. So you start by first defining your symbolic input, which represents the features that you'd be using for training. Then you actually instantiate the model itself, which is this function we saw in the previous page, creates the model. Then you define the criterion that you'd be using for training your model's parameters. You specify the evaluation criteria. You combine these to now form your training model. So this is basically doing what you were doing using the BrainScript network builder section of your config earlier, right? But now you do this programmatically. Then you instantiate this text mini batch source, which is basically the source of training data that would be used for the training. And this is the equivalent of the reader section that you had in the config earlier. Now you instantiate this trainer object and you tell it, this is the model I'm going to train. This is the criterion or the training loss function that I want to use to optimize the parameters. And this is the learning algorithm that I'd be using, right? So in this case, we are using the momentum SGD learning technique. And after having instantiated this trainer, we have this core mini batch loop where you take this mini batch source, get mini batches one at a time, pass them to the trainer. Internally, the trainer takes this mini batch, computes the gradients for that mini batch, passes that to the learner, which updates the parameters using whatever learning algorithm it implements, and you go on and on until you decide to stop. Right? Alternatively, you have this higher level form to train where you don't write the loop yourself, but the loop is now encapsulated inside this function, and instead of now passing actual mini batch data, you pass it the entire mini batch source, and you pass this training control which tells it when to stop. And it may not look like a lot of savings in this simple example, but if you were doing distributed training, this function would actually save you a lot of boilerplate code. So now let's take a quick tour of the actual API itself. Again, I'm not going into too many details of the API. I mean, this would be very well documented when it comes out in a couple of months. But these are the four. So the idea behind the API is to create composable abstractions and allow users to freely compose these different things together, right? So the idea is that all of these four abstractions represent various aspects of model training and definition. And users can optionally implement their own mini batch source or their own function and still use the other built-in mini batch, the other built-in facilities like the learner can be used from the toolkit, and you can have your own tensor operation, or you can write your own data reader but use the built-in functions and learners inside the library. Sure. Yeah. So the core abstraction here is the function abstraction, and this basically is your model definition. It's a computation graph, and it also represents the neural network that you would be training. It has a set of bound parameters, and it's a graph where each of the nodes in the graph are the base primitive level function operations, right? So let's actually look at this using this example. So now you have this simple a function which contains one primitive operation. So this is one function. This function has two inputs. So it has one set of bound parameters without the projection weights. It has one symbolic input, which is the features that are being projected by this times operation, and it has one output. Now you can create a higher level composite function by applying the plus or the bias operation on top of the output of the times operation. And now this resulting function has two sets of bound parameters, one input and one output. And now you can apply the nonlinearity to get a fully connected layer function. In terms of the compute API, as I said, the new library allows you to implement your own tensor operations. So it is highly recommended that you try to implement tensor operations by composing the built-in tensor operations that the library provides. But sometimes you might want to implement your own tensor operation that cannot be expressed using any of the built-in facilities, right? So suppose if you wanted to implement some funky training criterion that cannot be composed using existing functions, you can write your own function, and then you can compose it with the other built-in functions to form a higher-level network, which now uses both the built-in functions as well as your own function that you implemented outside. And how these things interact is through these forward and backward methods. So the forward method on the function is basically like the function call operator, right? So you had a function, say f of x, which defines your model, and now you actually pass the value in the forward method for the symbolic inputs to perform the computation given these values of the inputs. The backward method does the same thing, but except it actually takes gradient inputs at the roots of the function and then backpropagates it through the function and provides the gradient values for the inputs of the function. Right? So if you're just trying to evaluate, this is not interesting, but if you're trying to implement your own tensor operation that you would be using in training, then you need to implement this backward operation, because the gradients need to be flowing through not only through the built-in library functions, but also the own function that you implement yourself. I also mentioned earlier about new data interfaces being part of the library. So this value object is basically the data interface that allows you to pass in-memory data into the toolkit and also extract the computation results out of the toolkit. And this value object is basically just a glorified multidimensional array or tensor. I guess the part that glorifies it is that it has an optional mask, which means if you're trying to pack multiple variable length sequences together, as I was saying earlier, some parts of the tensor now would be invalid values. So you could use this mask to actually specify that you're packing things that do not fully completely fit the tensor. And then the toolkit would automatically take care of weeding those out when it does the gradient computations. And these value objects, again, can be created using your host language's native array types. So if you're working in Python, you can take a NumPy array and just create, which is basically a multidimensional array, and create a value object without any data copying happening between your native array and the value object that's created. It just sits on top of the same buffer without doing any copying of data. So this is what the function interface look like. If you want to implement your own, this is an abstract base class. You implement the forward and backward methods, where what you get are the values for the symbolic inputs of your function, and then you produce the actual values for the symbolic outputs of the function. and the similar thing for the backward method. So the library would provide itself a build about 50 or so primitive operations out of the box, and if you cannot represent your computation by combining these, well, you could write your own and use whatever code you want in implementing the forward and backward methods. So the next abstraction is a learner, and the learner encapsulates the parameter update algorithm that is used for updating the or optimizing the model parameters using the first order gradient values. Question? Okay, so the learner is just encapsulating the algorithm for updating the parameters using the first order gradient values. The trainer is the Uber driving process. So the learner is basically the momentum technique or the ADA-grad technique. If you have first order gradients, how do you update the parameters using those gradients? The trainer is basically putting everything together. So we'll see that in a bit as well. Sorry. So let's do it for the video. So again, the toolkit will offer several built-in learners, like the commonly known techniques for momentum, ADA-grad, etc. out of the box, and you can implement your own learning techniques by extending this simple interface in Python. So again, here's the learner interface. This is how you would instantiate the built-in learners, and if you wanted to implement your own, this update function is the only function you need to implement. So to read the training data, the abstraction here is the mini batch source, and again, the library will offer a built-in mini batch source that efficiently reads, randomizes, and provides input transformations. And it supports input modalities of various types like image, text, speech, and binary. And this built-in mini batch source is also capable of composing inputs of various modalities together. So if you wanted to create a multimodal task that uses both image and text data, well, you can use this built-in reader to create input streams of two different kinds of data together. And finally, users can, again, like the other abstractions, users can implement their own mini batch source by implementing this simple interface, right? So you just implement the getStreamInfos method, which advertises what are the inputs that this reader is going to produce, and this method that actually produces the mini batch data every time it gets called. And this is the final abstraction, the trainer, which basically puts all of this together. So a trainer takes a model, which is a function. It takes the learners, which are responsible for updating the model parameters, and it takes a mini batch source, which produces the training data, and it drives the core training process. And the trainer provides things like checkpointing of models and checkpointing the training state so that you can resume training from previous points if you wanted to. And finally, the trainer also supports distributed training. So when you're constructing the trainer, you can optionally pass a distributed train object, and that basically enables parallel training. The techniques supported are the same as we do in the current form of the toolkit, 1-bit SGD and block momentum. And you initiate parallel training by just launching multiple instances of the workers using MPI, just like you do today. Okay, so before we conclude this final thing, so this graph here shows a recurrent neural network model, and it's very similar to the feed-forward model that we saw earlier. With this one twist, it has this loop that basically represents the recurrence that goes through this past value node. So when you're defining this model bottom up, you have this problem that when you are trying to instantiate this times operation, one of its input depends on something that does not yet exist. So how do you represent this? So what you do is you define a placeholder, and then you take this placeholder, apply the past value operation on that placeholder, then you apply the projection on that output of the past value node, then you apply the bias operation, then you apply the ReLU, and now you have the actual hidden activation that you created the placeholder for. So now you can take this and say replace the placeholder that I created earlier to complete this loop. Right? So we are also considering having a high level form of this where you don't have to do this yourself. You can just specify the body of the recurrence, and then there will be a high level function that does this for you. So this is similar to Theano scan for those of you who are familiar with Theano. Okay, sorry, this was kind of a very quick run through and probably a lot of information in very short time, but are there any questions?